শেয়ার স্ক্রিন হ্যালো হ্যালো সাউন্ডটা বাড়িতে ওপরে ভলিউম আছে হ্যালো শুনে যাচ্ছে হ্যাঁ আসতে পারবে শুনে যাচ্ছে তো তাহলেই হবে ঠিক আছে ওকে
আমি তো ফোন করলাম তো ওখানে রয়েছে ফোন করছে এগুলো থাকলে অসুবিধা নেই এটা 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 দিয়ে এটা ক্লোজ করে বিষ্ণু, এখানে আরেকটা কি গুঞ্জা ছিল, ওই স্ক্যানারটা আজ লাগবে না? হ্যাঁ, তাহলে
তুমি অ্যানাউন্স করো না।
YouTube sorry.
Good morning, everyone. So, welcome to the day 3 of this Indocrypt 2022. And today, the first session is on Boolean functions. So, and the second here is Dr. Abhi Chakraborty. So,
Thanks, Nilanjan, for the introduction. So we are going to start the first session on day 3 Indocrypt 2022. The first talk will be on modifying bent functions to obtain the balanced works with high nonlinearity. And this work has been done by Shubhamoy Moitra, Professor Shubhamoy Moitra, Dr. Bimal Mondal, and Manmohan Rai. And the talk will be given by Bimal.
good morning to all. Now, I am going to present our work. This is construction of a highly nonlinear balanced Boolean function by modifying the Bain function. This is a joint work with Shubhamoy and Manmohan. These are the outlines. Our work may be divided into 3 parts. First part, we propose a new combinatorial characterizations of highly nonlinear balanced Boolean function. Mainly, we focus on the balanced Boolean function that achieve the nonlinearity strictly greater than the working bounds. And then we compare our result with existing results. And finally, we propose the new construction method of such class of function by modifying the Bain function. First, I present some basic definition and notation of the Boolean functions. Here, the set x is equal to n with a set of all binary strings of length n, A function whose input is n bit binary string, output is 0, 1, we call Boolean functions. A Boolean function can be immediately represented as a multivariate polynomial, and that polynomial is called as a normal form. Here, the mean a, the value coefficient mu a, this value is either 0 or 1. The degree of the Boolean functions is the maximum weight a, such that the coefficient is non-zero. So, if the degree is less than or equal to 1, such class of function we call it affine function. In the affine function is that if the constant term is 0, then we call it the linear function. The supported Boolean function with a set of all input that output value is non-zero, and its cardinality is all the weight of f. A class of function that weight is 2 raised to the power n minus 1. That means the number of ones and 0 are equal. Such class of function is called balanced function. The distance between two functions means the number of input they are different. That means the number, the integer that if we want to change their output, we move one function to another function. There's another concept that is called Walsh-Adams spectrum that is defined like that. And this is a very important spectrum value. It's a measure the different property of a Boolean function, like a function is balanced. We can only there was a spectrum where values at a 0 point is 0. If there was a spectrum value at a point a is 0 for all a, that weight is less than or equal to t, that case we call the function is t-resilient. Actually, t-resilience, if a function is t-resilience means if we a function a plus, if we add any Boolean function whose degree is less than or equal to t, that function becomes a balanced function. Another important concept that is called normality. It is to measure the distance between set of all affine functions. That means to provide the resistance of affine approximations. The relation between normality and Walsh-Adams transformations is that one. And for any Boolean function, if the normality is less than or equal to 2 raised to the power n minus 1 minus 2 raised to n by 2 minus 1. Because of that, the maximum absolute value of the Walsh-Adams spectrum is always greater than or equal to 2 raised to the power n by 2. A class of function that achieve this nonlinearity bounds, such function is called Bain function. Does the Bain function offer the maximum resistance to affine approximations? Although the Bain function are directly not used in the modern computer system because it is non-balanced, as it was at our spectrum at the 0 point is non-zero. The spectrum, the weight of the Boolean functions are it is 2 raised to the n minus 1 plus minus of 2 raised to the n by 2 minus 1. So we can easily construct a balanced function by modifying the Bain function. Just change 2 raised to the power n by 2 minus 1 output either 0 to 1 or 1 to 0 depending on the weight values. If it is a Bain function, there is an alternative equivalent condition is there that absolute spectrum value is flat spectrum, that value is 2 raised to the power n by 2. There's another concept that is called a linear code. We can linear code C with parameter NTD means that there is a 3-dimensional subspace of n and weight of any non-zero linear code words and all the code words non-zero code that is D. And the guarantee matrix is a binary matrix of order T cross n. In our paper, and for defining a linear code, we mainly focus on the minimum distance, but in our result, we need the minimum distance as well as maximum distance. So we define a special class of linear code that is called bounded linear code, and its parameter is n, t, min, and max. And it is defined as all that non-linear codes that lies between t to t max. And also we add another condition that there is at least one code C def such that the weight is either d min or d max. Constructions of a balanced Boolean function by modifying modifying the Bain function is quite easy. Just we need to change 0 to 1 or 1 to 0 and 2 raised to the power n by 2 minus 1 parts. But construction of such class of function with additional cryptographic property like nonlinearity is quite difficult. In this direction, first, in 1994, constructed a balanced Boolean function G by modifying the simple Manon-Fallon Bain function extra phi1. Actually, this Manon-Fallon Bain function can be written as concatenation of 2 raised to the power k linear blocks. and one linear blocks is all zero blocks. That's all zero blocks replaced by a balance function P. And then that prove that using this construction method, we can construct a balance function G, which is one just to get minus by 2 plus one maximum nonlinearity of balance function in n by 2 variable. It also claim that for any balance Boolean function in n variable, their nonlinearity is less than or equal to this to n minus 1 minus n by 2 plus maximum nonlinearity of n by 2 variable Boolean function, balance Boolean function. See, it is an open problem from last 30 years for n greater than or equal to 6. In our paper, we mainly characterize such class of Boolean function using the support set of Bell function. For that, we first define a matrix corresponding to any Boolean function that is called support matrix. That matrix, the dimension order is n plus O of F, and that column vector are the element of the support set. Like for example, if we consider the Boolean function in 4 variable that with support set have 6 elements, the matrix M of F is a 4 cross 6 binary matrix, and that column vectors are set with the elements of the support set with some particular order. We also define the partitions of the support set of any Boolean function with the partition of the support set into subset as ASF 0 at the point A, ASF 1 at the point A, ASF 1 at the point A means the set of elements in the support sets are that A dot x is equal to 1. Then you observe that the identity of the set ASF 1 at the point A is same as the weight of A times the support matrix for any non-zero A. And using this relation, we prove that weight of one set of spectrum and kinetic of the subset, kinetic of the subset, they satisfy this equality. So if F is a balance functions, then it is very clear that their spectrum value always multiple of 4. Using this relation, we prove that if a function f in n variable, then nonlinearity is greater than or equal to r, if and only if the kinetic of the set S at the point A, they satisfy this inequality for all non-zero n. And this is equivalent condition is that if such function exists, that means this support matrix is a generator of a binary of a bounded linear code with parameter 2 raised to the power n minus 1 n, and that the d min is r by 2 and d max is 2 raised to the power n minus r by 2. Now we consider r is that dominant bound value. That means r equal to 2 raised to the power n minus 1 minus 2 raised to the power n by 2 plus nonlinearity of balance n by 2. Then such function exists if and only if the weight of A times the support matrix that satisfy this inequality. This is equivalent condition is that function is exist if and only if that boundary linear code is exist. So actually we know the value of maximum nonlinearity of the balance Boolean function in n by 2 variable for n by 2 is 4, 5, 6, 7. So we write the conditions for n equal to 8, 10, 12, 14. For example, n equal to 8, the nonlinearity of the main function is 1 to 0, and for variable balance Boolean function, their nonlinearity is 4, and the upper bound is 116. But there is still an open problem: is the balance function exists in a variable with nonlinearity 118 or not? If that function exists, that means this inequality should be satisfied. That means the nonlinearity of SF1A there lies between 59 to 69 for all non-zero A, as well as there is a bounded linear code with length 1.8. The dimension is 8, and the d min is 59, and d max is 69. If such bounded linear code exists, then we can construct the corresponding balanced Boolean function. That nonlinearity is 118. Similarly, we can derive the other conditions. In this electrons, there are very few results are there. One result is published by Shorter and Moita in 2000 2000, and another result published by Maiti and Shorter in the FSC 2004. Shorter and Maiti, they claims that they prove that if the functions in age variable is balanced and non-negative 118, the function should have degree 7s, and the function can be written as concatenation of two small functions f1 and f2, where f1 and f2 are 7 variable functions, their degree is 7 and their non-negative is 55. And the function f1 and f2 degree is 7, so f1 and f2 cannot be balanced. So we further characterize and derive the property of the small function f1 and f2 so that we can reduce the start scale. Because if we want to construct the function here, there is the one way to identify the small function f1 and f2 that satisfies these two conditions. The converse part is not true, but it may be possible to identify the function, or it may be possible to construct such function. We will prove that the small function f1 and f2 therefore lies between 55 to 73, and the cardinality of the set is if I1 at chain on 0.8 satisfies this inequality. That means there are 5 here of support are there. Like if the support candidate of the subset of f1 is 55, then candidate of the subset of f2 is 73, because their sum is 128. It is a balance. So there are 5 possible pairs. But after that, the first 2 pair cannot be provide such balanced Boolean function with 118. So the remaining 2 pairs is and the remaining 3 pair can be possible to construct such functions. So in that case, we reduce the subspace. Another paper that is Mike and Motta in 2004, they proposed a construction method of such balanced Boolean function. For that, they first fixed that is a set of 8 elements whose elements are weight is 1. All element weight is 1. Then they search the suitable bend functions. That bend function satisfies the function 1 and 2. Then they prove that if we modify that bend function and construct that function g, then this balance that is non-negative is 118. But then the problem is fixed. And the question is that an is a such other t set is there. For that, we challenge the result, and we consider the t set outside the subset of AF, and that t set should satisfy this first and second condition with respect to the sign value of the function f. F is a bend function. Then the modified function g is balanced, and its non-negative should be 118. Here, if we consider that the t set is set of all elements of weight 1, that is the only one special case. So that case, we extend our subspace. So we consider all possible t set that is contain 8 elements outside of the subset of event function. And that paper they also derived another result, that is a result belongs to the one resilient construction of a one resilience function with non-negative 116. For that, they first to prove that to construct one resilient function with non-negative 116, we need at least 10 output. We need to change or modify at least 10 output. 9 of 0 to 1 and 1 is 1 to 0. Here the set is fixed. So we again generalize their result and derive the generalization. Yes, here the first condition is represent is one resilient function, and the second condition guaranteed that their non-negative is 116. We consider consider a different function in a variable. Yes, that is the main function. That is concatenation of 16 linear functions. Then we modify particular that bit output bit on 0 position, 8 position, 12 position, 247 positions, 10 positions. Then we get that function is 1 resilience, and then non-negative is 116. This is the different from the previous construction. Now, we present one construction method, that construction method based on the modifying the bend function. For that, we use a recent result proposed by Ms. Martin. And that result they claim that if n equal 8, and we consider the bend function that support coordinate of the support set is 120, and they prove that the coordinate of the set here set 1 at any non-zero point A, that value is either 56 or 64. That means the any non-zero combination of the row vector of the support matrix, their weight is either two values, either 56 or 64. So, if we want to construct a balanced Boolean function by modifying this bend function, we need to change at least 2 raised to the n by 2 minus 1 point. So we construct a T set outside the support set, and then derive the condition that T set should satisfy these two conditions for the non-linearity guaranteed that greater than equal to the domain bound. For example, if we consider n equal to 8, the support set coordinate is 120. The given bend function, then we construct another function g that is balanced. That is, we add 8 inputs outside the support set, and that 8 additional input satisfy the first and second condition. Then the corresponding function is a balanced Boolean function with non-negative 1 on 8. That means the support matrix of G, it is the concatenation of support matrix of A and support matrix of G. So for the previous result, we know the weights of the support matrix of M of A for any non-zero A. So we need to choose a suitable T such that the support matrix of MT, corresponding set T, that satisfies these two conditions. Okay. Unfortunately, the T set that their support matrix weight of any non-zero row vector is 3, 4, 5. Then we can construct such function. But unfortunately, we cannot identify such T set for n equal to 8. But if n equal to 10, that can be possible, because we can consider 10 binary strings of length. That weight of any non-zero linear combination is either 7, 8, or 9. That can be possible. But for the 8 case, we can consider 8 vector or 8 binary string of length that weight is 3, 4, 5. That is not possible. Similarly, for n equal to 12 or 14, we derive this condition, and it can be possible to identify such bounded linear code. In our paper, our main contributions is that to provide a combinatorial characterizations of balanced Boolean function that have very high nonlinearity, in particular to exit the domain bound. And we related that such function with bound a particular class of linear code. And then we could propose one constructions of such functions. And also we'll compare our result with the known one. This is still working on this paper. Actually, we observed that if we identify such a linear bounded linear code, then we can construct the balanced Boolean function with corresponding variables that exceed the nonlinearity of the bound. So I'm trying to identify such bounded linear codes. Thank you.
Thank you, Vimo, for this nice talk. I would like to request the audience, if you have any question, asking you still a few minutes. It's not.
This subject, I don't know. So maybe existable because we can consider 10 binary strings of length 16. Their weight is 7, 9, and 10. That can it can I don't know.
Or is there any other technique?
Support matrix method. Actually, I use the we can construct that balanced Boolean function with such nonlinearity using their basic was spectrum value. But that is difficult because in the converse part of the was spectrum, if I know the spectrum value of the 256 points with which are bound, then they are converse. It cannot provide a Boolean function. But this method, we can always guarantee that the converse, we can always construct a Boolean function. That's why we used the.
Any more question? Yeah. Anyone else? Okay, so let's thanks for Fikar again.
Thank you.
The next talk will be based on revisiting full tests on randomness testing using Boolean functions. And this talk, this paper has been jointly done by Dikshan Chatterjee, Rachit Parikh, Arpita Maitra, Shubhamay Maitra, and Animesh Roy. And the talk will be given by Rachit Parikh. So I would like to request Rachit. So Rachit is not here. Nilanjan, is Rachit giving the talk online? Okay, so we will try to shift this talk to the third one, and we can then start the next talk, which is based on weight-wise almost perfectly balanced functions, secondary constructions for all end and better weight-wise nonlinearities. And this work has been jointly done with Agnes Guinea and Pierre Munoz. So the talk will be given by Pierre.
No, my phone is here. And okay. So thank you for the introduction. And today I will speak about weight-wise almost perfectly balanced function, more precisely about some secondary construction and their weight-wise nonlinearity. And it's a joint work with Agnese Gini at Hamburg University. So first, let's talk about the motivation. So in 2016, with Journo, Standard, Carly, and myself, we presented a new paradigm of stream cipher called the filter permutator and a new family of stream cipher called FLIP. And this design is very particular for paradigm of stream cipher, and it's particular because it has been designed to allow an efficient homomorphic evaluation. That is to be used in complex protocol using fully homomorphic encryption. So the design is the following. It has three main components. So a large key register K, which is a binary key, a PRNG, which is public. The ID will be given, and the goal of the PRNG is only to derive some wire cross permutation. Yeah. So wire cross permutation are just permutation where we rearrange the order of the key bits. And then the last component is a filtering function F. It's a Boolean function from n variable to one variable. And to produce a key stream, it will work in the following way. For each key stream bit, wire cross permutation is derived publicly from the PRNG. The key is permuted, and the permuted key enters in the filtering function F. And then the result of that is stored the plain text in the ciphertext. So each time the only difference between each key stream bit is the permutation that we use, the wire cross permutation. And this gives a very initial situation for stream cipher, something that has not been observed before. Since we are just reordering the key bits, the Hamming weight of what enters in the function f is always the same. It means that the Boolean function f will not be applied on any element of f to the n, but only on elements that have the weight of the key, the same number of 1. And so since it's very different than before, it requires more analysis than what we saw at the beginning. And that's why in 2017, with Carly and Opela, we studied more particularly the properties of Boolean functions when they are restricted on a subset of F2 to the n and cannot be all elements of F2 to the n. And what we observed is that, in fact, in this context, for the vector permutator or for other paradigm of stream cipher, the attacks that are usually used, like to determine the security, such as correlation, cross-correlation attack, or the attack based on algebraic properties, they apply a bit differently. In fact, they can be made stronger when F is restricted to a subset. But on the good side, also the criteria that are used normally to determine the security, the ones that allow us to give bound to estimate the complexity of the attack, will also be useful here. Like, for example, usually we consider the balanceness, the nonlinearity, the degree, and the algebraic unity to see if some filtering function is good. And we will have the same when we restrict the inputs. We will have the same kind of filter. And for flip, so cipher in question, more particularly, we focused on the slices. So during my talk, I will use the term slices a lot. It's the slice EKN is a subset of binary vectors of size n having exactly K1. And the slices form a partition of the Boolean vector. And one natural question that came from this work is how can we do Boolean functions that have good properties on all the slices? So not only on F2 to the n as before, but independently on each slice. And so one of the first property we want for a Boolean function is usually to be balanced. That is to give 0 on half of the input and 1 on the other half. And when we go to studying the slices, the equivalent would be to have what we call the weightwise almost perfectly balanced function. And this is in fact a function which is globally balanced as before. And on each slice from 1 to n, we want the function to take 1 on half of the slice and 0 on the other half. And since the slices are cardinal, binomial, and true scale, all of those are not even. So when it's odd, we allow the function to take one element more leading to 1 or one element more leading to 0. And since 2017, many constructions of the WAPD function have been given. I'm aware of more than 10 words, as you can see. But one problem with this construction is that most of them are quite complex, like are recursively defined, and also they provide function only when n is a power of 2. This is a particular case of weightwise perfectly balanced function, WPD. And this case is a bit simpler because only the extremal slices 0 and n have odd cardinality. And now that we are considering functions that are balanced on each side, the next property that we would like is the equivalent of nonlinearity in the general case. Nonlinearity is what we use to track how it will be difficult for an adversary to approximate well the function by a mapping function. And in the case where we restrict it to the slice, we refer to weightwise nonlinearity or NLK. It will be the minimum distance between our function f and affine function g, but this distance is a mean distance taken only on the slice. So not on the whole F2 to the n as before, but on each slice. And so far in the previous work on the WAPD functions, there are some values that are given obtained experimentally, but n variables or sometimes in 16. And so far I'm aware only on 2 families where there are proven bounds on the NLK of this function. So very difficult property. So that leads to the roadmap of my talk. I will present 2 secondary constructions which are very simple, differently from a construction. And the simplicity also allows to bounds and they are nonlinear weight-wise nonlinearity quite simply. And then I will give some complex constructions and parameters. So what is a secondary construction first? We've got secondary construction where we take generally some function in n variables with non-property, and we provide a generic construction to obtain function with a particular property in more variables. So to present the two simple construction, I will quickly about some tools we use, and it allows to follow with high-level ideas. So the first tool is a restricted watch transform, introduced by Meshra in 2018. So it's similar to the one-shot transform that we saw in the previous talk, because at this time we don't do the sum over f2 to the n, but only on the sides. And this allows to define differently the WAPD function and to represent it a bit more easier. So on the recipe watch transform on the slice in 0 of the WAPD function will be 0. The cardinal of the slice is even, and it will be plus or minus 1 fits all. And since we force the WAPD function to be globally balanced, the number of -1 and 1 will be equal. And the remaining part of my talk, I will use this kind of representation for the WAPD function. So this is a vector of restricted watch transform in 0. And you can see that only 0, 1, and -1 for these functions, and the same number of 1. So the second tool that we use is the property of adding the symmetric function to a WAPD function. So symmetric functions are functions that take the same value over a slice. So more particularly, we will use a slice indicator function, PKN function. This function, the function PKN is the one taking the value 1 when the mean weight is k, and 0 everywhere else. And if we add it to a function, it will have this impact on the restricted watch transform of the slice. All the elements different than k, but the next k will remain the same, and we will just flip, like multiply by -1 as elements corresponding to k, as you can see here. And the last tool that we use is Siegenthaler construction. So it's a very simple secondary construction that goes from two functions in n variables f0 and f1, and with a function in n+1 variable that we call g here. And in fact, g will take the value of f1 when the last variable is equal to 1, and the values of f0 when the last variable is equal to 0. And the simplicity of this construction also allows to quite well what happens with this restricted watch transform. You can see that for the vector corresponding to g, we can obtain it from the one of f0 and f1 just by adding some particular coordinates of these vectors. So just before presenting construction 1, I define a subfamily of weight-wise almost perfectly balanced function that we call special, and I will present a swap function. So in the particular case of the WAPD function where we force the 1 to be for the weights which are lower than n over 2, and the -1 for the weights which are higher than as you can see in the example. And as a first remark, you can see that any WAPD function can be turned in a special WAPD function just by adding some slice indicator function. That is just changing some 1 into -1, and it works also because the total number of 1 and -1 is always the same. So the first construction goes from any two n variable swap function to one swap function with n+1 variable. And the high-level ideas of the construction are the following: it's to use Siegenthaler construction with two swap functions, and then to track the values of k so that slices k and k-1 are both odd cardinality. As you can see on the example, for these particular values of k, we just add the two functions, just combine the Siegenthaler function. We will have some 2 and some -2 in the restricted watch transform. So it will not be a WAPD function. So what we do is, in fact, we will correct these values by adding slice indicator function to the function f1. That is, we will flip the one or the minus one that we're supposed to lead to 2 or minus 2, and this way we obtain more zeros in this part. And we can see that the obtained construction is a special WAPD. Okay. And since the values we need to track, the values k only depend on the parity of the binomial coefficient, it's independent of the function. It's a property that comes with n. So it's the same construction for all the time we want to use. So now construction 2. It's a construction that goes from one n variable swap function to a step function in more variables. And the idea that we use simple construction, but the time is twice the same function. That's why we need only one swap function. And then we will iterate t times the construction 1, keeping this property of using always the same function. And with this very simple construction, in fact, we can obtain bound from the NLK of the function we create. And this on the fact that there is a direct link between the respective Welch transform and the weightwise nonlinearity, and because there is a very simple expression of the respective Welch transform in single-term construction from the one of F0 and F1. So this gives the following bound. That is that the respective nonlinearities of the function g are obtained as function of the nonlinearities of the function f, the function we use as a seed in the construction. And now I will provide some information on concrete construction and parameters. That is based on the experiment we did, like taking already known function in a small number of variables and using our construction to create function in more variables and test them weight-wise running. So the first family of function we consider for that function from the paper 2017 from Carlet, Popela, and myself. This was the first construction of the WAPD function. It's recursive, so we provide a function for every n. And in the case where n is the power of 2, there are some bounds on the NLKs that have been provided by Sue last year. And in this paper, we were able to prove that, in fact, all these functions are naturally special WAPD functions. So it means that we can directly use it in construction 2. We don't have to correct some term before by adding symmetry functions. And so the experiment we did were to take the CMR function in a d variable and to use construction 2 until getting 16 variables. And here are some examples of the function we built and their respective nonlinearities. And you can see that these functions are better depending on which slide we consider. There is no best function directly. The second construction that we consider is the one from Liu and Ménager of 2019. It's a very different construction because they consider the transform over the big field F2 to the n. And in fact, it's a family of functions that they create this way and not only one construction. But it's only defined for the case where n is a power of 2. And one main advantage of that construction is that we can provide lower bound on the NLK of this function. And also when we test it in practice in a low number of variables, the NLK obtained is very high. And we did different tests, and we did more on the paper. The most important one is the second point here, where we take we choose between the 8 variable function of this family. We took the one with the highest NLK, and then we apply construction 2 to go up to 16 variables. And these are the 2 different kinds of functions we obtain from an M function using this procedure. So the last kind of concrete construction that we did is what we call the hybrid construction. So the principle here is to build a WAPD function slice by slice. like taking for each slice the support of the slice from another function having a INLK on this slice. And to do that, first we know that we can use opposite slice, since the slices K and N-K are strongly related. In fact, if we have a function f with a particular value of the restricted nonlinearity in the slice N-K, we can create a function g having the same value of the restricted nonlinearity, but on the slice K. So it means each time we have a high value in two opposite slices, we can take the biggest one. So what we did after is to compose from different functions, so taking for each slice the best one we obtain from the test we did before using CMR function or event function. And you can see here with one example of a CMR function, another derived from ln. It's not always the same as the highest NLK, so we will just take the maximum and combine it to do a new function. So this way we obtain a function that we call H16, which is so far the function the WATB function in 16 variable with the highest NLKs that have been observed. Quickly about the code, our code is public on GitHub. And, the principle is that this way you can retrieve all the different functions we talked in the paper and more. And also you can test their parameters. And the main goal of making it so public is that we would like other persons then to test the function on the new construction of WAPD function you can have, and also test their weightwise nonlinearity. Now I will quickly conclude. So during this talk, I presented two secondary constructions of the WAPD function. These constructions are very simple, way more simpler than this construction, and they allow to form the NLK of the produced function from the values of the NLK of the seed function. I provide some examples in 16 variables here, and there are more in 8 and 16 variables in this paper. And I showed how we can exhibit a function with higher NLKs and this. And during this work, some open question arose. So the first one is that even if H16 has higher NLKs that have been observed before, it's still not reaching the bound. Coming from a former work, this bound is non-constructive. We know that some function reaching it exists, but we don't know how to construct this function. So we would like to see how we can change H16 to reach at least this bound, or if we need to go from totally different construction to get a higher NLK. And the second open question is about the impact of adding symmetric function on other parameters. Considering special WAPD function, we saw that when we add some symmetric function, it's not changing the fact that the function is WAPD. It's not changing its NLK, but we would like to see how this impacts the degrees, the algebraic unity, or the nonlinearity of such function. So that's it for my talk. Thank you for listening, and I will be happy to take some questions.
Thanks, Perry, for this nice and precise talk. So I'd like to request you, if you have any question, you can ask him. Any question? No question? Okay. Thanks, Perry. So we can start the next talk. Unfortunately, we have to stop. Yeah, we have to swap the talks, the second and third one. So we are now going to start the talk based on revisiting Boole test on randomness testing using Boolean functions. And this work has been jointly done by Dikshan Chatterjee, Rachit Parikh, Arpita Maitra, Shubham Maitra, and Animesh Roy. And the talk will be given by Rachit.
It's not here. Yeah. Yeah.
You can take the slide changer.
Sure.
Okay.
Yes.
Mobile motion.
Hello everyone. So this is a joint work with Vishen Chatterjee, Pida Mehta, Chuan Mehta, and Animesh Roy. So we'll be revisiting Moon Test today. Moon Test was a paper that was presented in SECIP by SIS in WEC. And I'll just briefly go through the problem statement that we are going to target here. We have to determine non-randomness in a binary stream. We will be given an input binary stream, and using Moon-based strategy, we will be dividing the input data into n different blocks, and then define Boolean function over that blocks, and then we'll test this over a metric called Z-score. So our main problem statement that we have targeted and solved here is that we have found an efficient algorithm to find the best Boolean function or the Boolean function with the maximum Z-score. So the outline of the talk will be, I'll be first introducing some basic terms and why are we doing randomness testing. And I'll just go through some definitions on Z-score support. Then I'll just briefly explain what Moon test algorithm actually does and how we are going to improve that. Then some preliminary results that will be helping to formulate an algorithm for that. Then our algorithm that we designed, and then some results. So security of protocol lies on randomness provided by the pseudo-random generators, and a small seed. Usually the methodology is that a small input will be there in this particular PRG, and based on that it will output a bit stream. And what a randomness test does is that it tries to find a pattern of the bits or pattern of block of bits, and from that particular pattern, we'll be trying to find non-randomness. So this is statistical randomness testing where we'll be checking out the distribution of block of bits or any function on block of bits, and then we'll compare it with the same distribution that is coming from suppose and random data or assumed random data, and then we'll say that the data is not random if it differs like significantly from the random data, the data we have assumed to be random. And Moon test actually assumes A has to be random, so from that we'll continue. First, I will define support of a function. Support of a Boolean function will be like the inputs for which the output will be a non-zero value. So fx will be 1, and we also define wf to be those inputs for which, so let's say I have a bit stream like given below, like 0, 0, 1, 1, 0, 0. This is the input data that I have been given with, and my block size is 2. Then you can see here it is my I, the set collection I, and wf will be those elements in this I that will be giving me non-zero value. So again, I have defined QF and BF. It's just the proportion of the cardinalities of these sets. And now we define the Z-score. The whole paper is targeted towards improving or increasing the Z-score or finding the best Z-score. So the Z-score is nothing but the proportion of ones that we get from the input bit stream. And it's the difference between the proportion we get from the bit stream and what if the data was truly random, like truly uniform. The difference is the Z-score. Like intuitively, you can see that. So I'll just show an example of computing the Z-score. So let's say I have been given this 20 bits of data to me, and the block size was 2. So the number of occurrences are given here. the proportion are also here. So 0, 1 is coming with input probability. Then we try to define functions. So there are a total of 16 Boolean functions from 0, 1 m to 0, 1. And we have calculated the BF support and everything for those functions. And we observe that the maximum, we get the maximum Z score for fx is equal to x2. So it's a Boolean function with the maximum Z score. So our problem statement lies in finding this particular function efficiently. We cannot go through all the 2 power n functions. It would be like practically we can just go for n is equal to 6, but after that it would be pointless. So we try to design an efficient algorithm that can find it in short time. So yeah, also one more thing. So a Boolean function f shares the same Z score with its complement. It can be seen clearly. The QF will be changed to 1 minus squared for its like complement, and this it's symmetric down there. Then PF would be 1 minus PF dash, QF would be 1 minus QF dash. It's very simple to see. Complement and it both will have the same Z score. So what bool test does actually is that it will try to find the Boolean function with the highest Z score, not the highest usually. And this function will act as the best distinguisher. So I will be having a relation between bits, and what I'm trying to do, what bool test tries to do is that it will give a function that will just capture non-randomness in the data better than other functions. So the bool test is invoked on some assumed random data in AES in this case, and the region and reference window is stated. I will come to that point after some time. And that is said to be random if the Z score obtained is is inside this reference window. So I'll show the reference window once. So this is the reference window. So these are the Z scores obtained by running AES several times. And if your input stream falls within this, so these are the parameters of bool test, different parameters of bool test. And if your data falls within this range, then the data is random according to bool test. So I'll just go to the algorithm once. So what they do is that they just first take the, I'll just show an example. So let's say I have this particular bool test with, they'll find all the Boolean functions with degree 2. All of the function will have degree 2 in each of the monomial, and there would be k is equal to 3, total 3 terms in this polynomial. So like they are trying to find a very small subset of Boolean functions that will satisfy their properties, and then you can see here in the first step what we are doing is we are finding all degree 2 monomials and then computing their Z score. And the next step, top 5 monomials will be considered, will be taken, and then their combinations, their k is equal to 3, their combinations will be taken, and the function with the maximum Z score out of the final 5C3 combinations will be your best Boolean function according to this. So it's just searches through a small subset, as you can see. Like there are 2 particular criteria, and after that, we'll not be able to find the best Boolean function. It computes Z score for all functions, so it's a little bit inefficient because if you start doing it for every Boolean function, then it will take 2 power m time. So we try to solve both of these problems. We'll just find the best Z score as well as we'll do it efficiently. So for that, I'll just define some preliminary results. So let's define RF to be the difference between PF and QF. So I would just like to say that in this particular slide, the Z score, as you can see, there's some observation here. So QF is just what is coming from the uniform data. So if there is a way that we can fix this QF and just see and just focus on PF, then it would be easy to like eliminate many functions here. So if we fix QF, we just need to maximize the PF, and PF we already have from the data. So using that intuition, what we do is that we define a RF. RF would be the just the difference between PF and QF. And what we claim is that if we maximize RF, then we have maximized the Z score. So FT is the set. FT is the set of all Boolean functions whose supports cardinality is T. The size is T, and the set of all Boolean functions can be 0 to 2m. It will be the whole set of Boolean functions. Now there's an observation that if we have to maximize the z-score from this particular set ft, then the function has to satisfy this property. So it should belong the input at which the function is supposed to give 1 should be the t most occurring inputs, or it should be the least t occurring inputs. Then we'll be able to maximize the RF. You can see here, I written that the same thing. The RF, if you want to maximize RFT, then you will either maximize or minimize the PFT, since the QF is fixed. This t by 2 power n is fixed in this particular set. So how we'll be able to maximize this, and we also show that it's not necessary to minimize it, because minimizing PFT is equivalent to maximizing PF 2 power m minus t, because z-score of a function and its complement is the same. So we'll just find once we calculate for all 0 to 2 power n, like that's the most inputs that can give you 1. So once we do that, we'll be able to find the maximum z-score, like maximum RF. And once we got the RF, then it's just plugging in the values. So we were able to compute the maximum z-score in m into 2 power m time. Okay. So can we do better? So this is the algorithm. Like this is just the algorithm that I just stated. I'll just show an example. So this is your input data. It's the same one as previous, and there is 20 bits. Block size is 2. So we just sort by the occurrence. Like 0, 1 is coming the most number of times, so it will be the first one, and then we just add their sums. So let's say t was 0, the number of ones for 0, then it would be 0. Then if it was 1, then it would be 0.4, then 0.7, and so on. So we do it for each number of ones. So maximum, there are 4 inputs can give you 1, because the Boolean function is a 2-input function, and you get these values RF t dash, and you see that for t is equal to 2, we get the maxima of RF t dash. So for t is equal to 2, you'll get the best Boolean function. That I know. I can easily find out by this. I can find out the function by this condition, this particular condition. And by doing that, we come to the same conclusion that the Boolean function would be fx is equal to x2, that we got previously through brute force. So now, so you can just solve these linear equations to get the function, and we get fx is equal to x2. So time complexity here is O(n) to just first just go through all the blocks, and it's O(n), and then to sort the probabilities, it would be taking m into 2 power m. Space complexity would be 2 power m, because we are storing all the values in the truth table, and it's not feasible for a large block size because security parameters are usually 128 bits, so should not do this. So we can we further improve this? So before that, we'll just go through some other So if m is equal to 28, then we'll just have to store this 2 power 135 bits. So the main observation here is that for a large block size, not all inputs will be there. So let's say my block size was 128. So not everything will be there in the input file. Every block won't be there in the input file. So let's say there are only t distinct blocks in this file, this particular file, out of 0 to 2 power n. Now, what we claim here is that increasing t, the number of ones above d, is not required at all to compute the maximum z-score. The maxima can be achieved till 0 to d. That's what we claim here. So let d be the number of distinct blocks that appear in the data, and zt be the highest possible z-score for a function. Then we claim that the z-score of f of d, that is the maximum z-score that you can obtain in a function fd, that is for all the functions that outputs exactly d ones, would be greater than j for all j greater than d. So we prove this because we see that this is a decreasing function, can be seen from the graph. See here that zfd would be, in terms of h, you can write zfd. Zft also you can write in terms of h, because the number of ones will be constant, because since not every block, there are only d distinct blocks, you cannot have more distinct blocks, so there is no possibility of getting one in the data file. So that's why it should be n. the number of ones in the file. So you get root n h t by 2m, and since this is decreasing function, so this will be less than, the z score will be less than this. So using this observation, we come up with like another algorithm. So yeah, so t will be considered in d, which is just on, because we are just going through the file and there are d distinct blocks. So d is less than n. The truth table representation of a function takes 2m place because we just like completely show it through a truth table, but we use another encoding here. So encoding scheme would be just, we'll just show those inputs for which our function will be returning 1. Other things we won't show. So these representation we'll be using for our particular algorithm. This will require only ON space. So this is our algorithm that I stated in the, yeah, you just have to sort all, you just have to check through. It's the same algorithm as the previous one, but we just have to check from 0 to d. So, and d is less than n. So yeah, this is the algorithm. It's just the details. So yeah, so we run this algorithm on RC4 to find the second bit bias. We compare our algorithm with the bool test, and the best Boolean function that should be giving us the best Z score should be the function that will be giving 1 for all 0 input and the rest output should be 0. So we actually found that. So our this is our comparison between the bool test, the original paper bool test, and our bool test. So B1, B2 are the original paper ones. The Z score, as you can see, obtained was 4.55, 4.47 for different parameters, and we got 64.16, which was the best Z score. Same for RC400 MB, 643 we got. We changed the block size. So yeah, these were the parameters that we used. So as you can see that bool test is not able to search through all the function space, as well as it's taking time because it computes Z score for each individual function. So similarly, we show the same results for AES and Java random. So as you can see for Java 10 MB file or like 256 block size, for different block sizes, we get like significantly higher Z scores, very high actually. Yeah. So okay, so the conclusion is that we are not commenting anything about the randomness test here. We are not going to go through like the statistical randomness testing here. The main intention here was to just increase or maximize the Z score. Because the Z score, we don't believe it to be a good metric here, since like we can just consider a file where 0 to 255 are written exactly once in the sequence 0 to 255 in their binary representations. Then the Z score obtained for any Boolean function with block size 8 would be 0 in this case. So we believe that Z score might not be the best metric here in such cases. So we optimize the 2 power trivial algorithm to the n log n. N log n would be required to sort the inputs according to their probabilities. And our modified bool test will give you the best Z score. So again, I'll just repeat my point that we are not commenting anything on the statistical randomness testing provided by this, but we are just focusing on improving the algorithm. If it turns out to be a good test in future, then we have an algorithm ready for it. So yeah, that's all.
Thanks, Rashid, for your really nice talk. Do you have any question?
So I have one question is that is there any connection between Z score of the data and entropy? Because I am seeing that counting Z score, the first step is counting the occurrences. So I think there is you can draw a connection between Z score and entropy. Do you?
No, I actually have read that entropy is used in some randomness tests, but I'm not sure like how we can connect it. But yeah, we can just look at it.
Oh.
Any further questions? So if not, then let's sign the speaker again.
Thank you so much.
And this talk concludes this session. And now we will have a tea break and we'll start the next session at 11:20.